All right, well, I'm going to go ahead and get started. Thank you, everyone, for being here. My name is Dan Mangum. I'm a software engineer at a startup called Upbound. We're still a relatively small startup, but I wanted to kind of give some context about why I'm here, because I think this talk is going to be pretty different from most of the talks you're going to see at RISC-V Summit this year. Primarily because I don't have a background in computer architecture or design or anything like that. I'm primarily a software engineer. The company I work for does not work in the hardware space. It doesn't even work at the hardware-software interface space. We're mostly kind of in the cloud-native community, if you will. But I'm going to be talking about a project that we started and is part of the Cloud Native Computing Foundation, and also kind of the problem space and how it may relate to RISC-V and some of the changes that have happened in the hardware industry. So the real reason why I'm here is because we have a huge problem. And I don't just mean me or the people in this room or even just the cloud native community. Mostly the whole technology industry has a huge problem. And when I talk about this problem, I like to bring up this picture. This is a picture from the AWS console where you can basically search for all the services that they offer. I'm not sure if this was taken before or after reInvent last week, but if it was before, that 227 number, which is the products that they have here, are likely more like 300. That's the pace at which new products are being offered. And I want to be very clear, I'm not picking on AWS here. I'll use AWS as an example through most of this talk, but that's primarily because they are the first and ostensibly the most used cloud provider. I also want to be clear, this is not a slight on cloud providers. I would say that cloud providers are probably one of the biggest drivers of innovation over the last 2 decades in the technology industry. So very appreciative to the work that they've done, but I do think we have a fundamental problem here. But to kind of give some context for this problem, I'll start with a short history of the cloud. And I call it short because relative to a lot of the topics at this conference, like microprocessor design, the cloud does have a very short history. It's about 2 decades old, maybe less than that. And most people point to the start of the cloud at its earliest stage as the founding of Amazon in 1994. So Amazon was founded as a digital bookseller, and right from the beginning was fairly successful by most metrics. Successful enough that by 1997, they were able to IPO and become a public company. And from there, they continued to grow and grow and grow. And being a early digital business, right, they had to scale very quickly. And what do you need to scale as a digital business, right? You need servers, right? So they had a bunch of servers that were coming, or a bunch of users and customers that were coming to their store, and to be able to accommodate that, they had to reach a scale of compute services that previously was kind of not possible or not done before by a business of that size. And as part of building out this competency, right, they decided in the 2003 range that it might be useful to actually take what they'd done to be able to scale their business and allow other organizations to scale in similar ways by buying some of these abstractions that they had created in front of infrastructure provisioning. So a lot of folks think that AWS built the best infrastructure abstraction, and that's why they've been massively successful. I would say that is not why Amazon was successful. The reason why Amazon was successful, or is successful, is because they built a competency for building infrastructure abstractions. So it's not that they found the magic bullet for building an infrastructure abstraction, it's that they were able to react and build new abstractions and adapt to whatever was going on with their business and build abstractions that made sense there. But importantly, and we'll talk about this more later, when you buy products from AWS, you're not buying the competency, right? You're buying the abstraction itself. So kind of taking a step back and maybe comparing the growth of the cloud industry over the last 2 decades to something in the hardware space, I'd like to talk a little bit about how some of the cloud migration for organization looks a little bit like some of the things we've seen with Moore's Law. And I'm not going to get way too in-depth, right? I'm sure most of you probably have more familiarity with this than I do. But Moore's Law, essentially means that we double the transistors every 2 years in an integrated circuit. This was proposed by Gordon Moore in 1965 and then revised in 1975. And it, along with some other laws, such as Dennard scaling, have allowed over a period of time for us as software developers to kind of get exponential growth in performance without really innovating on the software side of the stack. It's not to say that there hasn't been innovation on the software side of the stack, but it is to say that if we didn't innovate, we still got a lot of massive gains, or a free lunch, you might say. So how does this relate to cloud migrations? Well, let's look at a chart of the transistors in integrated circuits over time. And you'll see here that we have a y-axis that's a logarithmic scale. So if you put a trend line right down the middle of this, being on the trend line indicates exponential growth. And a lot of folks believe, and this is backed up quantitatively, that if you look specifically at Moore's Law, that we're starting to kind of fall off that pace of double the transistors every 2 years. There's lots of other factors. I'm not going to litigate all of those up here, but this is kind of the general sentiment and one of the reasons why RISC-V has started to gain adoption. And so what are kind of the components that are analogous here in cloud migrations? Well, when you first migrate to the cloud, and in the earliest days of the cloud especially, there were kind of these core services. So there was compute, like EC2 instances on AWS. That was RDS, a managed database solution, right? These kind of core fundamental primitives of an organizational infrastructure architecture that they were able to move and allow someone else to run them for them. And that had kind of a step function like growth and productivity for those organizations. As you continue to adopt the cloud, and as more cloud providers have sprung up and offered more and more services, you begin to move to higher levels of abstraction. And I would argue that these higher levels of abstraction are offering only marginal gains compared to that first migration. So if we looked at an extremely simplified chart, much less quantitative than the one we just looked at, we once again have organizational velocity here on the y-axis at a logarithmic scale. And what I mean by organizational velocity is kind of a proxy for a number of different attributes you get from cloud migrations. One would be typical velocity you'd think of in terms of just delivering features faster on your product, but it's also a proxy for things like cost and performance and that sort of thing. So what I'm illustrating here is that we once again kind of have a trend line of this exponential growth. And as you adopt these core services like EC2 and RDS, you really are getting probably above that exponential growth. But as you continue to adopt, you start to fall off that trend line. And you stop getting as much gains, as much organizational velocity as you did from the adoption of the previous. So what will hardware companies do? What will cloud providers do to stay on this trend line? Well, they'll fight tooth and nail, and it breeds competition, right? And this is a really good thing. This is how we get innovation in the industry. So definitely positive that we're trying to stay on that trend line. So what are the differences between the hardware and software analogy here? Primarily it lies in the techniques to stay on the trend line. Some techniques in hardware over the last decade or so that have allowed us to stay closer to that trend line as the number of transistors and the transistor density has fallen off a little bit is a system on chip, right? So there's been kind of a growth of this term actually in kind of consumer vernacular because of things like Apple Silicon and the M1 chip. There's domain-specific accelerators, which I know a lot of folks who are interested in RISC-V have an interest in. And a good example of that would be Google's tensor processing units, which are useful for machine learning workloads. And then there's actual transistor innovation as well, right? So we've moved from things like FinFETs to gate-all-around technology. There is still advancement happening at the transistor level as well. And these things are helping us to continue to derive performance and get those gains even when we start to reach physical limits. So what are the techniques that cloud providers use to stay on that kind of exponential growth trend line? Well, the first thing they'll do is provide access to better hardware, right? As hardware innovations are made, you can consume those via cloud providers. So a lot of those advancements that are made at the processor level eventually flow up to the consumers from the cloud. I think a great example of this recently is AWS offers some ARM Graviton processors, and they have extreme performance benefits over the x86 EC2 instances they were offering before. I believe they actually just released a new Graviton design at reInvent last week. Another thing they do is they integrate services with existing services, right? So kind of the more AWS you buy, the more you get. That obviously has some lock-in downsides, which we'll talk about in a minute. But in the short term, having integrated solutions is really beneficial for consumers. And the last thing they'll do, and we've kind of already touched on this a little bit and we'll go into more depth, is they'll offer higher and higher level abstractions. So you have to have less domain knowledge and less concern about what is happening behind the scenes of this abstraction that the cloud provider offers you. So the real difference between this set of techniques that hardware vendors use and this set of techniques that cloud providers use is that the switching costs from a software perspective, right, for a software developer's perspective, is relatively low to consume hardware advancements. So typically, right, as we said, you could just get a new computer and it would be faster and you can run the same code and get better performance. That's not the case for most of these options from cloud providers, right? There's really high switching costs, especially if you're going not just between services on a cloud provider at different levels of abstraction, but if you're going between cloud providers themselves. So why is this true? Software interacts with hardware through a series of layers. I'm sure folks are all familiar with this. There are compilers, there's the instruction set architecture itself, there's operating systems, right? There's differing levels of abstraction, but we can drill down through those levels of abstraction because we have a common interface that we're targeting. RISC-V is kind of attempting to be a single interface for heterogeneous hardware, which is becoming more and more important, right, as we start to encroach upon physical limits. And that extension model provides allowances for evolution over time as well. So with RISC-V, right, there is a small subset that's the base, and you can continue to build out extensions. There is some ratified extensions. There's also vendor-specific extensions, a really flexible model to continue to innovate at that level. But all of these abstractions are eventually targeting the instruction set architecture. Cloud providers are also heterogeneous, just like hardware, but they don't have a common interface. And we'll have a visual of this here in just a moment. But the problem that this introduces is that when you move to higher levels of abstraction, you can't drill down lower, right? Raising the level of abstraction is actually raising the lowest level interface as well. So if we wanted to visualize kind of a comparison of what the hardware-software interface looks like and the cloud interface looks like, it could be something like this. This is obviously a very simplified diagram, but what I'm illustrating here is that we have an interface with the instruction set that's targeted by a variety of levels of abstraction that live above it, but we have access to each of them, especially if they are open source. So if you put the interface or the integration level right below RISC-V, we could say that you can innovate below the interface at the hardware level. You can innovate above the interface at the software tooling level. And because of the extension model of RISC-V, you can also innovate at the interface level. So this is not true for the cloud interface. It looks much more like this. And what we're illustrating here is the levels of abstraction are much higher for some of these services. So a good example is comparing something like EC2 and Lambda. Lambda is a function as a service, managed service that AWS offers, where you're essentially giving them your source code and they're doing the rest. EC2 is your more traditional VM kind of situation there. But you can't drill down through Lambda, right, to get through the layers and get to EC2. They give you one interface to Lambda and one interface to EC2, and they're deciding what the interface level is, and you can't really cater to your specific needs there. So instead of having kind of this flat interface that you're eventually reaching, it looks more like this, much more rocky landscape, much harder to adapt to your specific organizational needs. So I said before that what made Amazon successful and what makes Amazon successful today is that they have a competency for building infrastructure abstractions, but that's not what you buy when you buy products from AWS. So why don't they just sell you the competency? If that's a better product, they could ostensibly make better margins on it, and it would be a win for the industry, right? Well, there's a couple of reasons. First of all, it is very difficult to package competency as a product, right? It's much easier to package that abstraction up and offer that as a product. You know, one of the kind of like magical things about software is that you can write it once and with little to no modification, it can be consumed by many, many different people and organizations. And that's why there's so much money that flows into software, right? Because you kind of have this fixed cost and then potential ability for, you know, infinite scale of consumption there. Another reason why they wouldn't sell you the competency is born out of deep domain knowledge. And you'll hear cloud providers say, and this is probably a fair statement, that they have some excellent domain knowledge. They have really good domain knowledge in running compute, running databases, et cetera, right? That's why they've been successful. That's why people pay them to run these services for them. However, I would argue that there is a difference between having deep domain knowledge and knowing how to run compute and deep domain knowledge and knowing how to consume it. And the latter there really only being something that an organization itself can dictate, right? They have the best domain knowledge there because they're the ones consuming. Last thing here is successful companies evolve rapidly and unpredictably. And AWS has a lot of customers, right? They don't just have one customer. So when you change and to some unforeseen event to be able to continue to grow your business and stay relevant and survive, AWS may not choose to change with you, especially if you're not their biggest customer, which is another thing we'll mention in a moment. Importantly, these last two here become more pronounced at higher levels of abstraction, meaning that if you are operating at a higher level of abstract service on a cloud provider, these are even more likely to bite you as a customer. So where does that leave us? What are our options moving forward? Well, one option would be to sell training to each organization, which this is something that, you know, consulting companies do and that sort of thing, and help them develop that competency themselves. Well, that's not very scalable. Software is more scalable than human beings are. Also, it's extremely inefficient. The reason we have cloud providers, the reason cloud providers are successful is so that not everyone has to have an AWS-sized business inside of their organization, right? If everyone did that, a lot of businesses wouldn't exist, first of all, because it would be so capital intensive, but also there'd be a massive inefficiency in the market, right? Another option, and you'll see this happen actually quite a lot with very large, successful companies, is just to commit to one cloud provider and roll with the punches. That has some massive issues. At the beginning, you might have a large special contract that's just made for your organization that has some really good cost modeling for you. But once you engage in that, and the deeper you dig into that cloud provider, the more leverage you lose in negotiating any future contracts, right? If you're completely reliant on a cloud provider for all of your infrastructure, a single cloud provider, you have no leverage in that conversation anymore. And this is also another thing that I mentioned earlier. If you are not their biggest customer, then you are always at the mercy of the bigger customers, right? They will dictate the roadmap because they provide more revenue to the cloud provider. It's not really rocket science, but you know, it's just the way business works. So the third option, and this is the option that and the makers of the Crossplane project, which is what I'm going to talk about here in a moment, is to create a common interface, kind of similar to what RISC-V is trying to do in front of heterogeneous hardware. And one of the key things to being able to do that is making it modular, right? If RISC-V was not modular, then it would be susceptible to the same kind of legacy constraints that we've seen from other instruction set architectures that hold them back over time, right? We need to have a small, simple subset, which is the core, and allow folks to continue to build on top of that without restricting future growth and innovation. The last thing is, it's not only advantageous for this system to be open source, it's required. Anything short of that means that you no longer can access those different levels of abstraction that we saw earlier in that hardware-software interface stack, right? The compiler level, the operating system level, et cetera, those become opaque to you, and you're operating more at that commercial company dictating the level of abstraction to you. So what would a system like this look like? I'd imagine it would look something like this, where the cloud providers are essentially becoming analogous to the heterogeneous hardware that lives below our instruction set architectures. And we have this common interface that we can target, which once again allows for innovation below the interface. The cloud providers are going to continue to build amazing services that provide a lot of efficiency gains to organizations. It allows for innovation above it. You can build abstractions on top of these common interfaces. And if it's modular, you can innovate at the abstraction level. So I mentioned earlier this project Crossplane, which is a CNCF project. And it is built on top of Kubernetes. Kubernetes was started as kind of a container orchestration system, but it's really grown into more of just a distributed systems framework. Why is it important to be built on top of Kubernetes? From a distributed systems perspective, Kubernetes is becoming kind of like what Linux is for an operating system, in that you can kind of get a Kubernetes API just like you can get a Linux API almost anywhere. So being built on top of that means that we can do this infrastructure provisioning almost anywhere. It also means that we get all the properties that a robust distributed system already has. If you're provisioning infrastructure, this is a long-running operation. It's not like compilation to binary source code, right? It is something that happens continuously, right? Your infrastructure is running. It has to be reconciled. This has to be a scalable system so that your organization can handle more infrastructure provisioning over time. So that's why we have kind of chosen Kubernetes as this layer to interact with. And I mentioned at the beginning I'd leave this on a bit of a cliffhanger, right? I'm talking more about the problem than the actual solution. That being said, this solution does exist today, and it's an ecosystem that's growing over time, and we're starting to build these levels of abstractions that sit above it. And what you're really moving towards here is almost having a sort of internal cloud provider per organization, but reducing the friction so that you can also take advantage of what the cloud providers offer and the great work that they do, right? It doesn't mean that we're moving all the servers into our own closet, in the office. It means that we're building on top of these cloud providers, but we have an interface that allows us to easily switch between them, switch between layers of abstraction, and build our layers of abstraction on top of it. So the last thing I would say, I know I'm getting close to end of time here, is to come join us. I mentioned at the beginning that this is not like most of the talks you're probably going to hear this week, right? And one of the reasons I wanted to come and present here, number one, I personally am a big fan of RISC-V and am very invested in the community. But number two, I think that all of y'all have expertise that you can offer, right? I made this parallel to the changes that have been made in the hardware industry and how they need to also take root in kind of the cloud native ecosystem as well. And so I hope that folks in this room and folks watching online or folks who watch this later feel like they can come and add to this community as well. So thanks for being here, and love to answer any questions.
Megan Walks from Sci-Fi. Maybe it's not a question, but maybe a like quibble with a term that you used. So you said that it's essential that this be open source. And I think one thing that RISC-V got right is they're not, that what's open is the standard, not the implementation. So is there a standard that goes with Walks that you were showing? Oh, sorry. Anybody here?
Yeah. I could hear it just fine. I guess I'll repeat it in case of folks didn't. Yeah, so the question was, is there a standard that goes along with what we're doing, right? What RISC-V got right is the standard is open source, but there can be both open source and proprietary implementations. And that's a really great question. And yes, there is a standard, and there's actually a whole set of conformance suite and that sort of thing, so you can build your own implementation. There is a kind of cross-plane standard, and there's already multiple implementations of the API itself. That's actually another thing. We're being built on top of Kubernetes, which has a standard API that's implemented by lots of folks, including all the different cloud providers. You can get managed Kubernetes offerings there. So yes, long story short, there is a standard that you can implement. Crossplane itself has an implementation similar to how Kubernetes has an implementation of the Kubernetes API. All right, well, thank you everyone for coming, and hope you all have a great week.